Alright class, in this video we're going to be looking at the law of gravitation, how gravity affects large objects like planets and suns. I was reading a book about anti-gravity recently. I just couldn't put it down. It's so interesting. Here's a nice quote of the day. If I had seen farther than others, it is because I've stood on the shoulders of giants. Sir Isaac Newton. Shoulders of giants means that he got a lot of the information needed to make his laws based on previous scientists like Robert Hooke and others to help with his laws of physics. Sir Isaac Newton was perhaps the greatest scientist of all time. He actually helped invent the reflecting telescope. He used a lot of math in his equations, so he needed to invent calculus to make sure that his math was adequate. He also connected gravity and planetary forces together. The main works that he published were the Philosophiae Naturalis and Principia Mathematica, which is still used today in a lot of math classes and calculus. Here's a quick overview of the acceleration due to gravity. This is actually on the previous unit when we looked at kinematics. So you have a person over here and he drops the ball. This shows where the ball is located each second. You notice that as it gets further and further down, that's because the ball is actually accelerating. It accelerates about 10 meters per second squared. It's actually 9.8 meters per second squared. That means it goes 9.8 meters the first second. It goes 9.8 more than that, or about 19.6 meters per second, the next second, and so on. The higher you drop a ball, the greater the velocity will be at impact. Also have more force on the bottom. So Isaac Newton did discover that gravity plays a vital role in determining the motion of the planets. It's a concept of action at a distance. So we knew beforehand from Aristotle, Copernicus, and other scientists that planets and stars were in motion. Isaac Newton actually made the calculations to help determine how the motion of the planets actually go. And here's our main law of gravitation. Your force due to gravity is equal to capital G, that's a constant, and it's not 9.8. This number is actually on your formula chart. And the number for big G is 6.67 times 10 to the negative 11th power. Really small number for G. The reason why is it has to do with the mass of the first planet times the mass of the second planet in kilograms, and then inversely, or divided by the distance squared. As two masses get further and further out, your denominator is going to get bigger. Whenever you divide by a bigger number, you're going to get a smaller force between them. Okay, so imagine the Earth and the Moon has a fairly strong gravitational pull, but if you look at the Earth and a star that's many light years away, you have a much different force due to gravity. Another thing to do when you're actually calculating these, you want to use parentheses in every number. The reason why is the M1 will probably have 10 to the certain number exponent, and you're doing that twice. The way that I put them in the calculator is parentheses, the G number, times parentheses, whatever your mass is the first, times parentheses, mass of the second. I like pressing enter at this point, then divide by, in parentheses, whatever your distance between the planets are squared. Write that number down, and then write the top number, your numerator, divided by the bottom. That's the safest way to get your correct answer. If you try to put all the numbers in at once, you'll probably make a mistake somewhere in your order of operations, which can make dramatically different numbers. Also, make sure that you put the E, or 10 raised to whatever number, whenever you get your final answers. Here's some applications of gravitational motion. If you look at the tides are due to the gravitational pull of the Earth and the Moon. At certain times of day, the Moon's actually closer to the Earth. That's when it bulges towards the Moon. When the Moon gets away from the Earth, the tides go opposite, and that's where you get low tide and high tides, right? Since gravitational force decreases with your distance squared, the Moon's pull on the Earth is the strongest on the side facing the Moon and weakest on the opposite side. The Earth actually gets stretched along the Earth-Moon line because of the force due to gravity. The oceans will rise relative to the land at these specific points. Tides actually cause friction in the Earth. So because Earth rotates and spins around, the rotation tries to pull these tides along, but the tidal bulges of Earth didn't rotate. Essentially, the fight between the Moon's pull and the Earth's pull causes friction. The Earth's rotation actually slows down about 1 second every 50,000 years, and that's due to the tidal waves. You could also look at orbital energy, escape velocity. Orbital energy is essentially the total energy you have of a planet. That'll be equal to the kinetic energy, how fast it moves, and the gravitational potential energy. That has to do with the energy due to other planets doing gravity. Orbits cannot change spontaneously. It takes time for them for the direction to change. An object cannot crash into a planet unless an orbit actually takes it there. An orbit can only change if it gains or loses energy from another object. So that's why when we have meteorites that are coming towards the Earth, other planets and our moon could actually change the orbit of these meteorites very dramatically. Even a small difference, many, many miles away from Earth, could make it not even hit Earth at all. Alright class, so that concludes the video on gravity and gravitation. If you have any questions, feel free to leave a comment down below and shoot me a message.